So what I'd like to do now is a video on how to do ray tracing for a concave mirror, so concave like this, where the mirror is on the inside, and a real image, so concave and real. When we have curved mirrors, we want to be able to figure out where that curved mirror is going to create an image. So when we're doing this, the things that we need to work on, we need our axes. We need to figure out what is horizontal to us. We also need to figure out what is vertical. And I recommend that you draw a straight line behind the mirror and treat that as the mirror. It means that things will be a little bit cleaner when you're doing your ray tracing. Now I marked the center curvature here, and halfway between the center curvature and the mirror is our focal. So let's see, centimeters. Let's see what we've got. I have 30 centimeters, so the 15 is right there. So I'm going to mark my focal point right there, and then I've got my center curvature marked. So the things we need to start with: horizontal axis, vertical axis, the center curvature, and the focal point. So that's where we're going to start with our setup. I put this right at eye height. Should do that differently next time. So let's put an object in front of the mirror. Now an object, I'm just going to use a little circle. All right? And it could be anything. It could be you, it could be a light source, it could be a piece of paper, it could be anything. It's just an object that's going to be in front of the mirror. So I'm going to label this as my object. And then I've got center curvature. Okay, this is our setup. So you're going to be given something similar to this, and you have to figure out where is the image going to be formed. So where does this mirror create an image of this object? And the way we do that is with ray tracing. And there are 3 rays that we use, so I'll go through each of them in turn. The first one, oh, blue is not going to work. The first ray is out parallel to the axis and then through the focal point. So if you remember the definition of the focal point, light rays that come in parallel all go through the focal point. So there's going to be a ray that goes out parallel to the axis from the object, light leaves the object, hits the mirror, and now you see I'm going to go to this back line here. And then when parallel rays come in, they exit through the focal. So I'm going to do this. All right, might need to extend that a little bit. Something about right there. Okay, so that's our first ray. The second ray goes through the focal point and then goes out parallel to the axis. So it's kind of the second definition of the focal point. An object, a light ray that starts at the focal point, leaves the mirror parallel. So if we have something going through the focal point, let's see here. So it comes out of the object, goes through the focal point, hits the mirror, and then it's going to bounce off the mirror parallel to the axis. So something like this. So that's how it's leaving the mirror. And then the third ray. Our last ray is a ray that goes through the center of curvature. And then let's figure out where that comes out. If I have a light ray that goes through this point, goes through the center of the circle, and it hits the mirror, it's going to bounce back immediately on itself. So it's not going to shift direction at all because it's going to be hitting the mirror absolutely perpendicular. So our third ray is through C, and then it just goes back on itself. It's kind of easy. All right, here's number 3. So we have a light ray that leaves the object, goes through the center curvature, bounces to the mirror, and then bounces right back off again. Okay, those are our three rays. And look at that. All three rays meet right here. So this point right here is where our image is formed. So the image is formed here. And now we can see a couple different things about the image from our ray diagram here. This is my horizontal axis. My object was above, my image is below. So if this was a person, for instance, then they would be looking like this. All right, so upside down. That matches with what we saw in the big curved mirror. Your image was upside down. And the image looks smaller. Okay, that matches with what we saw as well. So the image is inverted and smaller in size. So the things that we can say about the image, so the image is inverted and it's smaller than the original object. Now we can actually measure where this image should be created. So I'm going to have to measure a couple different things. The equation we had, I'm going to get a better, okay, the equation we had for curved mirrors, 1 over dO plus 1 over di equals 1 over f. All right, so what are these things? dO is the object distance. So this is the distance from the object to the mirror, and it's parallel to the axis. So it's the total, just the horizontal distance. So here's my dO is going to be from object to mirror. So dO is going to be this distance here to here. In this case, what do we have? I've got about 53 centimeters. So my dO is 53 centimeters. di is image distance. So how far the image is from the mirror. Everything's measured to the mirror. So image to mirror. And again, it's parallel to the axis, purely horizontal. So my image distance is going to be from here to here. di is going to be this distance. How much do we have there? 21? Yeah, 22. So that is 22 centimeters. The third one is the focal. So that is from the focal point to the mirror again. And here, yep, we've got 15. That's what I had before. And so I'm having an image formed 22 centimeters in front of the mirror when I have an object 53 centimeters in front of a mirror of focal length 15 centimeters. So ray tracing is a good way to get a close estimate of where an image is going to be formed. Now, to get a better calculation, we want to do the numbers here. So I've got 1 over dO, and I want to solve for di here. Now let me give you the formula in a one-step method. In your calculator, di is going to be 1 divided by, parentheses, 1 divided by focal minus 1 divided by dO. So if you put this in your calculator, one step to calculate the image distance. So in our case, 1 over the focal, which was 15, minus 1 over dO, which is 53. And that number, when you calculate it, should be pretty darn close to 22 centimeters. And since I don't have a calculator with me, because I just made this up, you'll have to do that calculation on your own. Hopefully it's right. So 1 over F minus 1 over dO gets us di. The last part that we can figure out is how tall the image is. So we have an object that has a certain height, and clearly the image is smaller, but how much smaller? We can calculate where it is, and we can also calculate how tall it is. The equation we've got for that one, and I'm going to erase these, is the magnification equation. Magnification is just a number saying how much bigger something is from its original. So if my cat was 4 times smaller than me, okay, she's way smaller than that. If my cat was maybe 10 times smaller than me, then I would say the magnification factor is 1/10. If my husband outweighed me by double, he doesn't, then the magnification factor there would be 2. So this magnification, since it's smaller, I'm going to expect a magnification that's less than 1. So a magnification factor less than 1 is going to give me something smaller. A magnification of 1, same size. Magnification more than 1, bigger than the original. The magnification is calculated with knowing the image distance and the object distance. And it's defined as the image height over the object height. So we can actually figure out what the magnification factor is. All right, so in this case it's minus DI 22 over DO 53. Well, darn it, I don't have my calculator. So we'll have to figure out what that is. Go to it. Okay, and so that's going to be some number. It's definitely smaller than 1, so that's good. And now that negative. What does that negative mean? Well, if you think back to when we've seen negatives in Physics 1, often it was telling us other direction, like the negative direction. So that negative sign right there tells me it's inverted. So the inverted means a negative magnification. It's flipped over. Smaller than 1 means the image is smaller than our original. And if I know how tall the original object is, then I should be able to calculate the actual image height. So HO is going to be measured. How tall was my object? So HO is the purely vertical height to our axis. And I get 12 centimeters. HI, okay, if I go here, let's just bring that HO to the other side. It's going to be the magnification factor times my original height. Oh boy. So it's minus 22 over 53 times 12. I'm not doing that in my head, folks. So we calculate it at a certain amount, so whatever that number is, negative something, and then we can measure it from our picture. So measured, what do we get from my measured? It's just about 5, I'd say. And it's negative because it's flipped over, and it was about 5 centimeters. So hopefully, when you calculate this, you get something very close to 5. And your numbers aren't probably going to match up perfectly, and that's okay. The ray tracing is merely an estimate. It's a good estimate, but the ray tracing is to figure out what's happening. And, you know, is it inverted, smaller, that sort of thing. And it's going to be around here. And then we use the math and the equations in order to get the true value. So 3 rays on the ray tracing to get an estimate, and then the 2 equations to get the true values. Hopefully they're close. That's one of the ways you know you've done things right. If they're way off, if I calculated this to be minus 20 and it's actually minus 5, I probably did something wrong. So it's a nice double check that we can use to say, okay, we probably did it right. Okay, that's all I've got for curved mirrors, concave mirrors, and real images.